alle sammen, og velkommen til Betongcast med Norsk Betongforening. Nå det jo en liten stund siden... Det kom bare en beskjed. Nå det en liten stund siden vi har hatt Betongcast, men nå vi I gang igjen, og dette den første I dette året her. Vi har planlagt et par andre også, en I mars og en I april, så dere må følge med på betong.net, så får dere greie på temaer fremover, og det også lov å komme med forslag hvis dere har noen gode temaer dere synes vi bør ta med på Betongcast. Denne sendingen her som dere har oppdaget I vanlig Teams-møte, og det betyr at dere må ha av kameraer og ha av lyd, og det har dere også stort sett, så det bra. Men det gjør også at det mulig å stille spørsmål underveis. Da kan dere enten stille spørsmål I møtechatten, eller dere kan bruke den rekke opp handa-funksjonen, og så gir jeg dere ordet underveis. Nå det jo sånn at vår ene foreleser ikke snakker norsk, men det lov å stille spørsmål på norsk hvis du ubekvem med å stille på engelsk, så har Tor Arne Hammer lov til å oversette, enten da til engelsk eller tysk, ettersom hva du finner for godt der og da, Tor Arne. Vi har jo et spennende tema, karbonarmering eller karbonarmert betong, og vi har med oss Tor Arne Hammer fra Sintef Community, og vi har med oss Mathias Tietze fra Technische Universitet I Dresden. Og begge to sitter faktisk I Dresden, så det jo litt pussig. Tor Arne vel litt grann koronafast egentlig. Kanskje. Yes, da det sånn, jeg har lyst til å dele med dere helt til å begynne med en liten presentasjon om Norsk Betongforening. Skal vi se. Da må jeg jo spørre om dere... Det kan jeg jo egentlig ikke, skal vi se. Ok, Tor Arne, jeg har dempet deg da, men kan du bare bekrefte at du ser skjermen min når jeg viser den? Skal vi se. Tor Arne?
Ja.
Ja, bra, da hører du meg. Jeg mister jo alt vet du, når jeg går over til den andre skjermen. Da vil jeg bare at du bekrefter at jeg har med meg skjermen når jeg går over til den andre visningen her. Det veldig bra.
Ja, det fungerer.
Ja, så bra. Da skal jeg til og med gjøre sånn, tenker jeg. Ok. Da skal jeg bare si kort litt om Norsk Betongforening for dere som eventuelt ikke kjenner oss så godt. Jeg regner med at dere fleste kanskje kjenner oss I hvert fall litt. Vi jo en forening som for deg som arbeider med eller har interesse for betong og betongfaget. Og det et åpent medlemskap for alle som har interesse for faget, og man kan være personlig medlem, studentmedlem hvis man student, og det også mulig å være bedriftsmedlem. Og det jo en utrolig fin måte å bygge seg faglig nettverk på og være aktiv I en sånn type organisasjon. Så med å være medlem I Betongforeningen så får man jo tilgang på et stort nettverk, og det gir også en mulighet for faglig vekst og utvikling, og det veldig mye spennende man kan være med på. Det også en veldig bra ting at som personlig medlem så får man gratis nedlasting av publikasjoner. Det veldig nyttig og veldig lettvint måte å få tak I de på. Det også rabatt på tidsskrifter hvis man ønsker å abonnere, og for studenter så det gratis tidsskrifter, så det egentlig en veldig, veldig fin ting å være medlem. Det stor aktivitet, det 1200 medlemmer, det 9 regionale medlemsgrupper, og de arrangerer åpne faglige møter lokalt. Det har jo ikke vært så lett nå det siste året, men det mye planer for høsten. Da håper vi at det litt mer mulig. Ellers det jo en del nettmøter, og sånn som disse betongkastene jo egentlig litt til erstatning for disse åpne faglige møtene. Så det 7 ulike komiteer, alt fra internasjonal komité, miljøkomité, FoU-komité og så videre. Så har vi jo Yngres betongnettverk, som et nettverk for de under 35 som jobber med betong. Så arrangerer vi jo også en hel del kompetansekurs av de kursene som krevd i standardverket. Og også andre kurs og konferanser selvfølgelig. Norsk Betongdag for eksempel. Norsk Betongforening har en hel serie med publikasjoner. Alt fra NB1 til NB38, det jo ikke alle de som like aktive eller relevante, men det stor aktivitet, og det også en stor aktivitet på hele tiden å oppdatere de som finnes. Det også en rapportserie helt opp til rapport nummer 9 som kom ut denne uka her. Så det utrolig mye bra fagstoff, og det får du tilgang på, og hvis du medlem så får du laste ned alt dette gratis. Rapportserien nedlastbar for alle. Så alt dette bare å sjekke ut på betong.net, og det også et veldig bra tips å melde seg på nyhetsbrev. Det kan vel hende en del av dere på nyhetsbrev allerede, siden dere har meldt dere på denne betongcasten, men hvis dere ikke det, så det et bra tips for deg for info om liksom, nye ting som kommer da. Yes. Da skal jeg gi klassisk komme seg ut av sånn. Ok, da skal jeg gi ordet videre til Tor Arne Hammer, som har en introduksjon til emnet og litt sånn bakgrunn for hvorfor du foreslo dette som et tema. Så da skal jeg si vær så god, Tor Arne.
Takk for det. Jeg har ikke noe presentasjon å vise til, så dere får se på mitt blide åsyn og høre på det jeg sier. Dagens tema det karbonarmering. Og det jo selvfølgelig interessant, fordi at karbonarmering ruster ikke. Vi vet jo alle sammen at stålarmering det gjelder på grunn av sine mekaniske egenskaper som bidrar til å gi betongkonstruksjoner den nødvendige bæreevnen, stivheten, duktiliteten og dermed sikkerhet mot kollaps. Og dessuten så jo prisen relativt lav. Men den kan ruste altså. Og det gjør jo at betongkvaliteten og overdekningen avgjørende for levetiden av en betongkonstruksjon. Men det bidrar også til at CO2-trykket av og til blir unødvendig høyt gjennom at man må sette krav til vesetall og overdekning, som da igjen gjør at sementinnholdet og betongforbruket blir unødvendig høyt i en del tilfeller. Så rustfrie alternativ det interessant. Og det jo ikke nytt. Rustfritt stål har blitt brukt, har blitt prøvd. Epoxybelagt stål har vært prøvd, men aldri tatt helt av. Og det samme gjelder glass og basaltfiberarmerte stenger. Aluarmering, aluminiumsarmering på trappene. Gjennom et stort forskningsprosjekt som drives av Norsk Hydro. Der hadde vi faktisk en betongcast for noen måneder siden med min kollega Harald Jusnes. Fiberarmering det jo et alternativ, men det kan neppe danne et fullgodt grunnlag eller en erstatning for stangarmering. Der hadde vi jo faktisk også en betongcast for en stund tilbake, basert på den nye NB38-publikasjonen. Men nå gjelder det altså karbonarmering. Og det meg bekjent ikke vært benyttet i Norge i noen stor skala. Annet enn at vi kjenner det gjennom bruk som forsterkning av eksisterende konstruksjoner. Karbonarmering har fått stor interesse i Tyskland. Det faktisk i dag et stort nasjonalt program på gang med et budsjett på 70 millioner euro. Og det sier jo litt hvor stor satsing det Og da var det jo selvfølgelig naturlig for oss å invitere en representant fra den organisasjonen som initierte det hele, nemlig Teknisk Universitet Dresden. Og da går jeg over til engelsk. I would very much like to introduce Matthias Titze, representing Technical University of Dresden. And who has been a member of this team dealing with this huge national program for 5-6 years. And I'm very excited to hear what you are going to tell us about this exciting material. So please, Matthias, the screen is yours.
Okay, thank you so much. Thank you so much for this possibility to present something about our new material combination, and thank you for this warm welcome and this introduction. My topic today is carbon reinforced concrete material and the cube building. What the cube building is, I will explain it later. But the first point is, what is the motivation to build with a new material combination and a new material like carbon fibers? And there are, I think, a lot of motivation points today. First of all, the urbanization. You know this, the world population is growing, especially in the cities in Southeast Asia and also in all over the world, and they're called mega cities. And so we need new materials to save space in the cities. For this, a lot of people, they will live there. We think in 2050 will live 6.5 billion people in cities. Now it's 3.6, I think. So it will increase, and we need new construction materials for these challenges. The next point is the steel corrosion. The most used building in the building sector is steel and steel reinforced concrete, especially. But there's a whole lack in this material combination, because the steel and the concrete can be corroded, and so we don't reach the lifespan we expected in these buildings. The third point is the resource consumption. The building sector is responsible for up to 50% of the building or of the resource consumption worldwide. And the fourth point is the CO2 pollution. For example, the cement production is responsible for 6 up to 8% of the worldwide CO2 pollution. And so we can say, if you talk about a new thinking about the environmental and to save resources, you have to think also about a new way to build and construction sector. And so we have a solution for that, not the solution, but we think a solution for this future challenges, as we call it, carbon reinforced concrete. And here are 4 of the main essential advantages. We think you could construct very slim with this material. You have more usable space gain. For example, the carbon fiber is chemical inert. That means it doesn't corrode. So you need less material to save the reinforcements for corrosion. And the next point is, you see a comparison of 2 concrete beams. On the right side is a steel reinforced beam, on the left side is a carbon fiber reinforced beam, and you see it's much thinner.
Matthias?
Yes?
You're not showing your presentation, if that's...
Oh, sorry.
I thought you had like an introduction, and then you started to refer to the...
Sorry. Sorry
figures.
for
Yeah.
that. Sorry for that. Now you will see it.
Yes, and then if you do the presentation mode,
yes,
also.
it's not a problem.
Yeah, very good. Thank you.
I'm sorry for that. This was the slide with the motivation. These are the 4 points: urbanization, steel corrosion, resource consumption, and the CO2 pollution. And the next slide, in the same way, slim construction, non-corrosive, and here I think we call it resource effect. We need less material, up to 50% less material in comparison to a classical steel reinforced beam. And in the conclusion, we also save a lot of CO2. We have a CO2 reduction because we use less material, of course. We say it could be a mega trend in the building sector because it's possible to use carbon concrete in tunnels, in bridges, also in sandwich and facade elements, and also especially for the architects, they will like it for curved constructions. You see it on the right rendering. But we have do the step into the market or into the market. Yes, I can say it in this way. We have a lot of national technical approvals in Germany called allgemein bauaufsichtliche Zulassung. We need this to use this material in the practical use. We have, for example, one for limitation of crack widths, also a strengthening system for slabs, and for facade elements, also for sandwich walls with the insulation inside, and for a precast parking garage, and also it's new application for parking decks. What we can say about the carbon-free reinforced concrete and the material. First of all, we will start with the fiber itself. On the right side, you see the carbon fiber. It's a carbon fiber spool. This is the same material you find in airplanes or automotives, in airplanes in the wings, and automotives in the chassis. This is the same material we use from SGL Carbon or from Teijin, Japan. And it starts with a crude oil. This is the raw material. It's not a very resource efficient material now, but or ecological material. But in the future, the research says we could use lignin as a basic for the raw material. The next step is they produce a PRN precursor. You see it on the left side. This is the white fiber in this bottle. And this precursor will bring in a process they call pyrolyze. And in the other bottles, you see other colors of this fiber, and these are the steps from PAN fiber to carbon fiber. In the end, this raw fiber gets a sizing to bring it in a better way to produce it or to handle it in the textile process in the next steps of the value chain. So, the first idea maybe you have is carbon fiber and concrete. Concrete is, I think, a cheap material, and carbon fiber very very expensive. And yes, you're right if you think in this way, but we start in the 1970s with over 500 euros per kilogram, and we came over the space and military, sports applications, the racing, then aviation and energy sector, wind energy especially, for the rotor blades, also in the automotive, and now we are up to 15 euros per kilogram. And now it's interesting for the building sector, also increases the volume of the production of this carbon fiber. And so we think it could be a material that we use in the building sector. But if you think about it, 15 euros per kilogram, the steel reinforcement costs only €1 per kilogram, I think, and a steel reinforcement is so very, very cheap. And the carbon reinforcement, 15 euros per kilogram, that means 15 times higher price. But we say you don't have to came from the cost side. You have to compare the performance side, because the steel have a density of 7.8 and carbon only from 1.8, and so it's a quarter of the density of steel. You get 4 times more material, volume material. And also another point is the tensile strength. The steel has only 500 Newton per square millimeters, and the carbon is up to 3000. So we have a 6 times higher tensile strength than steel, and so it means 6 times higher performance in this part. So we say 6 times higher tensile strength, 4 times higher a quarter of density, and so we have 4 times higher material. We could say it's a 24 times higher performance factor. So we say now carbon reinforced concrete is competitive now to steel reinforced applications. And there are different reinforcements you can get. On the left side, you see grids with different mesh whites and different coatings, especially styrol coatings or epoxy coatings. The epoxy coatings are stiff. The grids are very stiff, and the styrol coatings are very flexible for curved applications, for example. And on the right side, you see different rebars. There are also 2 coatings or 2 matrices you can use, thermoplastic and also duroplast. And the main applications are for the new buildings. You see here a very thin facade element. It's only 2 centimeters thin, and with 2 layers of carbon reinforcement. On the other hand, you have an application for existing buildings is the strengthening method for existing steel reinforcement, for example, slabs. And you bring on this in the comparison on the left side the steel reinforced application, and on the right side the carbon reinforced application. So you see for the steel reinforced application you have to use 8.5 up to 10 centimeters of concrete, and for the carbon reinforced concrete application you use only 1 up to 1.2 centimeters. You need much less material, and it's very easy to bring it on, for example, a slab. You have a very short construction time, so I think it's a good alternative in this sector. Next point is, I show you some pictures, is the recycling of this material. We think it's a huge point to for the next and further steps to get into the market to solve this this question. What you see here is a jaw crushing of a carbon reinforced concrete element, and in our project we do some test buildings, and we used it to destroy this test building to bring it in a jaw crusher and to bring it into more demolition material, to separate this material, and we have a separation quote up to 99%. You could separate the carbon short fibers up to 4 or 5 centimeters long, and the concrete materials. We use for this to the separation airstream sorting method with its camera based. So we have a capacity for from 6 up to 10 tons material per hour we could separate. I think it's not a big industrial process, but I think it's a good start to show what we can do in this recycling topic. And after this, we have also thought about what we can do with the short fibers. And so we have also, after this separation process, a new process created to use the short fibers. It's a process from the textile industry. It calls textile grinding process. So we can create a recycling yarn, a RCF fiber or RC fiber with a load capacity, we think, or we know that has 60 up to 75% of the load capacity from a new carbon fiber yarn. And I think it's a good step to close the Stoffkreislauf, to close the cycle of the materials. So I have some best practice examples for bridges in infrastructure. Now it shows some pictures from pedestrian bridges, and also a strengthening of a bridge, and some other bridge projects we do in the last times. First of all, the first pedestrian bridge, it's a modular pedestrian bridge. It's a precast U-shell we created with only 3 centimeters thickness, and a preset, and I think it's a hybrid. It's a hybrid product because this modular pedestrian bridge U-shells will bring together with pre-stressed steel components. And we create 2 of them, one in a small city called Oschatz in Germany, and the other one in Kempten. It's nearly from Munich. It's near of Munich. And the first bridge was nearly 8.5 meters length, and the second bridge is 16 meters length. It's a double length of this bridge. It was a prototype, or there was prototypes to test this method of construction. The next step was also a pedestrian bridge. It's a pedestrian bridge in Albstadt. It's also in Germany. It's near Stuttgart. And it's also a U-shell, very thin, 7 centimeters on the side, and on the horizontal side, it's 9 centimeters thin. It's with a carbon fiber grid from Solidian reinforced, and we think it's produced as a precast element in one step. We think it's a very good example to show what this carbon reinforced concrete method could create. This bridge is only 40 tons. The weight is only 40 tons. The comparison in steel reinforced concrete is up to 30 or 32 tons over the double. Another application is platform elements for a rail station. It's also an application you can build faster and easier in the railway station area to create or to have less time to use, or I don't know the word, sorry, but it's not a problem. This is a railway station parts. You see it on the left side. So our precast elements they will use in these areas for example, railway stations. They shown like this. In Germany, it's typical, not in the cities, but all over the countries in small cities, and so it's I think a very good and very easy system for us to create very fast new platforms. Another part is best practice in building constructions. So we have also a lot of applications in this area, for example, facade elements, sandwich elements, and also this trenching application. First of all, I think it's beautiful. It's a historical, not steel reinforced concrete structure. It's an iron reinforced concrete structure from I think 19th century, and we used the method of strengthening to refurbish this historical steel reinforced ton bowl. It's also in Germany. It's in a small city called Zwickau in Sachsen. The next thing is much bigger. It's a strengthening of a concrete or steel reinforced concrete silo. It's a sugar silo with a diameter of 45 meters and a height of 70 meters. You could bring in 80,000 tons of sugar, and they have a problem inside with cracks, and another silo have also a problem with a fire inside, and so they have this inside of this silo. There's we use over 14 1,000 square meters of textile, carbon textile, to strengthen this building. We use 3 layers of this material, of the textile material, and with the thickness of 2.5 centimeters. I think it's a very interesting application. Another application is the facade elements. There are a lot of different facade element systems you can use. We have here big facade elements with a system of aluminium, and on the surface you see, I think it's very cool, a binary code put it in. We have also for this an national approval or certification to realize this in a big scale, these facade elements. They are, I think, only 2.5 up to 3 centimeters thin. This especially, I think, 2 centimeters. So another building, it's located in Mannheim. It's near Frankfurt in Germany. This is a building, an office building, and they use facade elements in combination with insulation and also a steel reinforced inner shell. So you have inner shell insulation and also a very thin outer shell in carbon reinforced concrete as a full precast element, and it's assembled on the construction site. Here are some pictures from the assembling of the elements and on the construction site, and finally the full building and the facade. Next point, what you can do also is use the multifunctional parts of the carbon or carbon fibers. For example, we use these for this carbon reinforcements, not only for the load bearing, also for heating the elements, especially for heating, for room heating and so on. And so we create very thin facade elements with an insulation, and the inner shell has also this function, this heating function. And so we put it in post-beam construction and bring it in like a window, and you have a classical facade system, and on the inside you have also a heating or the heating function inside connected with your electricity in your building. Next point, some words about the production. I showed you the classical way of producing a carbon fiber. The next point is how to produce a carbon grid. So it's like this way from the carbon spool. You have to transport it to a textile company. They create the grids. You see also the grid rolls on the next picture, and you have to transport it also, and then you can use it for whatever you want, for for walls especially, or other applications like this. This is a classical precast wall element, where also as a conventional, like a wall element in steel reinforced concrete. We could do it also in carbon reinforced concrete, a little bit thinner, of course, but the problem is we need a lot of material, of the carbon material. It's up to 40%. We need more materials because we have to cut it off like this. It's too much material because of the production dimensions. We can't do it in another way. And so we say it has to be more like this. We use the carbon fiber only on this points where it is needed, and not more. And so we have a method for that. We use for this a robotic from, for example, from KUKA to create these grids individual for the precast elements they needed. Now I have a short video for you. It's only a prototype. It's now it's a little bit bigger. You could also bring doors and windows in, but this is the principle of the method we would like to use to save material and produce less waste. The same process. Okay, the final grid. So the next point is the cube. Cube is our new idea to bring all the solutions and together from our big carbon reinforced concrete from the C-Cube project into one building. This was the idea, and we started with that to bring the walls and the concrete and all the sandwich constructions, the reinforced materials and so on into one building. And we started on the left side with this idea. We said, okay, a two-story building would be nice to bring all applications in. And we called it Cube because it was a cube in the first idea. But then we thought about it, and our colleagues, the architects, and also our engineers say, okay, let's demonstrate what is technical possible and what we can do with this material. And so the cube develops, and we developed the twist elements. These are two twisted shells. They are the roof and also a wall and all in between. So we show everything what is possible with carbon reinforced concrete. The next point, or the second part, is the box. This is like the cube, a two-story small building with laboratory rooms and rooms for technique and so on. And the third part is, of course, a glass facade that connect everything. So you can see another picture how it should be from all the sides, the concrete shells and the box and also the glass facade. And here, next point, the cross section from the building and especially from the roof. In the middle, you see a very small window there that brings the both twist elements together and brings also a lot of light into the building. A part of our development was the wall element development. We started from a classical concrete precast element with 44 centimeters, and our idea was to reduce more and more this construction space to use it as a space gain inside. And so we developed precast elements with an inner shell and an outer shell in carbon reinforced concrete, and also we used high performance insulations to reduce more and more the thickness of the wall. And now we are on 24 centimeters for a classical wall in a classical installation standard. I have some impressions from the cube as I think a bird perspective, and now here a view from the side, from the northwest side on the building. And now you can have a look in this building on the right side with the box, 3 rooms and also stairs to the laboratories. And we have also a presentation area in this building, and I think it's up to the 220 square meters to use for the laboratories and for the presentation.
Matthias, can I ask you a question?
Yes.
On the not that picture, but that one before.
This?
Yes. Then we see a very thin wall. How thin is it?
On the left side, you see a part of the twist. This is the last point is the wing. It's 4 centimeters, but it increases it increases, but in the end it's 4 centimeters. Is it okay or?
Thank you.
Okay.
It's very interesting. It's very interesting. Yeah.
I say a little bit later, a little bit more about the twist element. Something about our timetable. We finished the development phase and also the certification phase. It was a lot of work to do this. You see it on a timetable from November 2019 up to January 2021. And now we are in the realization phase, and we hope that we finished the building in December 2021, but now the weather is not our friend, but we hope we can realize it in this time. And yes. Next is our construction site. This is now the building pit. We are still in this phase. Parallel to this, we create our box precast elements in a precast fab in the near of Dresden. And now you see our reinforcements or reinforced materials from the different companies we use. They are always and they are all partners in our research project. Solidian for classical flat grids, and the company Wilhelm Kneitz, also a company. They produced meshes, but with a more flexible coating. And Schöck, as a producer from the Schöck-Comba rebars for this are for the connection of the two layers of a wall element, and also our partners from ThyssenKrupp and SGL, they have also special reinforcements for the cube building. On the next slide, you see the production of this precast elements. On the left side, you see the classical way to bring the concrete in the mold, and in the middle, how we handle the elements in the concrete plant. And the third part is, but this is not actually photo. This is only this is a hybrid wall. Inner shell is steel reinforcement, and the outer shell is carbon reinforcement. But that you can imagine how we handle it. I put this picture in. But we do it in the same way, but with other insulation, not with a classical mineral wool. We use high performance material from BASF, polyurethanes. It's aerogel based. So the next part of the building is the twist. These twist elements I showed you before. This special element. This is a roof and also a wall, and also in between. I think it's a lot of layers we have, because these elements are not only concrete elements, they are also a roof, and also have an insulation layer, and also have a weather shell, and it's a very complex module that we created for this building, with you see this green small blocks. These are the insulation between our you see this gray grid. These are concrete. We use the method of concrete shotcrete or spraying, if you want. We on the construction site directly, and this is the method we produce this twist on the construction site. So, and now this is the building we will have in the end of the year in Dresden. It's the cube. Finally, we hope it is in this combination, also in this colored combination, very white concrete on the twist shells, and also a very black concrete at the box. And we think it's a very interesting building that will be created in Dresden. And I think we are on the, we have to say, finish, on the finish or in front of the finish line. I think this would be a very good project to show what carbon reinforced concrete can do. And now this is my last picture. Again, the comparison between steel reinforced concrete beam and a carbon reinforced concrete beam. And so I will close my presentation. Thank you so much for your interesting, and I think I'm ready for questions if you want. I hope we have enough time for that. Yes.
Yes, we have a little time left, so
yes.
Hvis det noen som har spørsmål, så fyr løs. If you have questions, just raise your hand and I will give you the word. Eller skriv I chatten. Hannes, vær så god.
Yeah, first of all, thank you very much for the excellent presentation. Maybe I was not able to follow everything, but in the twisted part, you showed a sandwich structure
yes.
with concrete ribs.
Yes.
If I understood correctly, they are sprayed or shot. They're shotcrete.
Shotcrete, yes.
Yes. Is there any reinforcement? How do you assure the bond between this grid and the two shells? I see that the shells are tied together at the edges, but between the grid and the shells.
Yes, these two layers are connected with these. I show you the part. The shotcomber rebar. In the cross points of the concrete, there are in every cross point is a shotcomber rebar located, and the other parts, the ribs are not reinforced.
Okay, thank you.
Yep.
Hello, I have a question.
Yes.
What about anchorage of the bars and the connection between bars and concrete? I suppose there are no codes for this material.
No codes, no coating.
No, in order steel bar, you have a lot of friction between the concrete and the steel. But here you have a smooth bar, and you need anchorage systems for the end of the bars, don't you?
You mean this like the ribs of the steel rebars?
The mesh, I think, is not the problem, but when you use bars, you need a connection with the bars and the concrete, and you need anchorage to compare with the normal steel system.
I see you. Could you see the picture and the bars on the left side?
Yes.
This one?
Yeah.
You have also like the steel rebars. You have also bring in some.
Yeah, I see your point.
You see this. It's with.
You can't compare with the steel reinforcement.
Yes, of course. You could compare it. That is what we do, but we could use only the smaller diameter because we bring this modes in.
Yeah, but would you have you developed some codes to use for calculation?
No, not really the coding.
I say codes, European codes, for example.
Oh no, sorry. Yeah, sorry. Now I understand it. We don't have a code now, but we work on that.
I suppose so, yes.
We use also in every application we use in German it calls Zustimmung im Einzelfall a single certification for only this building we built.
Yeah, right. So because this is the first building you're doing,
Correct.
it's a research task.
Yes, it's
quite concrete. I have a project now where I want to use carbon fiber rods, and my problem is anchorage of the rods. So
okay.
do you have any rules or the codes, not codes, but have any rules that you follow for the
yes,
anchorage?
of course. We could maybe if it's possible, you could give me your contacts and I give you some informations about that. How we use this rebars.
I'm
for
very
the calculation and so on.
Right.
Jeg kan formidle kontakt, Jarle. Så.
Would be, it's not a problem, yes.
Yeah. Very good. I look forward to it. Yeah.
Thank you, Jarle. Rune, you also have a question?
Hi, Rune. Thank
Hello.
you for the presentation. I was wondering, the pictures you showed of the bridges earlier on.
Yeah.
Can I ask what kind of concrete mix recipe you used for those thin bridge elements?
This is a concrete. I think C80. I can't say it exactly.
No.
I can't say it exactly. I scroll to the slide.
It was an organic sort of bridge you showed. That was 18 meters, and the one in the picture was 8.5 meters.
This is. I think I know what you mean. This is the bridge. One of the first bridges I think they was built, and it was not a standard. It was not as this one.
This one, yeah, because it's only 3 centimeters thick.
Only 3 centimeters, yes, of course. It's of course a high performance concrete, but I can't say which one exactly. But I could give you this information. It's not a problem, but I haven't this now here. This bridge is created in 1996 or 1998, I think.
Okay.
It's a long time ago, and I could give you this information, but it was not a standard concrete or a standard concrete mix. It was a special thing we create in the laboratory. But I could give you information about
that's okay, but it's in UHPC or ultra high performance.
Yes, of course.
Yeah.
Yes, of course.
I have one more question, if I may.
Yeah,
Excuse
yes,
me?
you may. On the Tor Arne, did you have supplementary information on the bridge, or do you
Yes,
have a
this-
question?
It was not on the bridge.
Okay, then with the other question for you, Rune, and then Tor Arne.
Just
Yeah.
a quick question, because you said you were heating the walls with the carbon fiber reinforcement. Is the
Yes.
carbon fiber conductive? Does it, or how do you do that?
Yes, you could contact. What is these pictures or only laboratory
Yes, yeah,
pictures?
yeah.
This one, yeah, you could contact the carbon fibers, and then you could use it as a heating system, because you could bring yes, you could use it for that.
Okay, thank you. Thank you.
It's, there are also other applications possible, not only heating, it's also for data transport, and other ideas for switches in the walls and so on. You could use it, but this is more an electrotechnical part.
Yeah, but
from our guys.
it's
I'm not an expert in that.
conductive. Yes, yeah. Thank you very much. Thank you.
Oh, you're welcome.
Thank you, Rune, for asking. Tor Arne?
Yes, I just want to thank you, Matthias, for a very exciting presentation. It's really impressive what you're doing. I guess I know that you have a nice web page, so I guess we can find some more information there that may answer some of the questions.
Yes.
And I have one small question. You said something about the properties of the material, but I didn't catch the stiffness, the E-modulus. Do you have data on that as well? Which is quite important from a structural design point of view.
You mean especially the problems from the material, or?
No, the Young's E-modulus of the bars, carbon bars.
Okay.
You gave the tensile strength, but I didn't quite catch the.
Yes, but I think this information I couldn't give you now, but I didn't have this information here. What especially the ThyssenKrupp rebar have, but there is a data sheet we have. I could give you this if you want.
Yeah, okay, thank you.
This is not a problem, but the exactly number I don't have here.
Okay, thanks.
Okay, any other questions?
Jarle igjen.
Ja, vær så god, Jarle.
I just think that a rough thumb rule is to say that the E-modulus is close to steel. Some qualities are some higher, some lower, but compared to steel.
It's compared to steel, yes. So it's nearly in the same range.
Yeah.
So
Okay.
you have the problem between the high tensile strength and the same M module.
Tor Arne?
Yeah, if we still have the time, one more question. What about pre-stressing? Did you look into that, the possibility of pre-stressing?
Yes, pre-stressing is one of the research parts in our project, especially the colleagues from Berlin do this around Professor Schleich, Mike Schleich, and they create the first modular, I don't know the word in English, highway, it's called in German Autobahn, highway bridges for this, they pre-stressed. They produced pre-stressed concrete beams. Maybe I could show you a picture. I don't have this picture in my presentation, sorry. But yeah, this is not only an idea. They produced a beam with 22 meters length, and now for the real bridge they produce 45-meter length beams for a test bridge. Now.
Thank you.
Okay, we have time for one more question if anyone has a question. Okay, Rune.
Just a quick question: are these products commercially available in Germany? Can anyone, producer, manufacturer, purchase and implement them in their products?
Yes, you can buy the rebars from, for example, ThyssenKrupp, what I showed before, and also the grids that is available, and the concrete matrix. You can use your concrete matrix with a little bit modification for that, especially. Yeah, you could use your concrete matrix, of course, and all parts are available now. I think on the market. Yes, but in Germany you have the problem you can't build with that very easily. Certifications to do it. So, and Eurocode, or we don't have DIN certification and so on. So we need special certifications for every building.
Okay, thank you.
Kan jeg blande meg inn litt igjen?
Thank you. Ja, very quick then, Jarle. Vi er på overtid.
Ja,
Vær så god.
Bare veldig kort. Sto og altså rehab-bransjen i Norge bruker jo karbonfiber i betydelig grad. Og Sto og Sika er jo de to største leverandørene av karbonfiber i Norge. Så der får man både nett og staver og alle produkter som vi har sett i dag, tror jeg, stort sett.
Så det er en del produkter tilgjengelig allerede også i Norge.
Ja.
Takk skal du ha. Takk skal du ha. Okay, thank you so much, Matthias. This was very interesting, and thank you for coming all the way to Norway. Og tusen takk til alle sammen som har fulgt oss. Da blir det sånn at dere får tilsendt presentasjonen sammen med en evaluering, og så det også sånn at vi kommer til å legge ut opptaket på betong.net, så da kan dere bare følge med der. Matthias, maybe before we close the meeting, you could write the web address, your website address in the chat, so that people can find your website. Så får vi med oss webadressen som Tor Arne refererte til også. So thank you very much, Matthias, og tusen takk alle sammen. Og så ses vi neste gang det Betongcast.
Thank you very much. Goodbye.
Tusen takk. Thank you.
Thank you so much.
Bye bye.
Takk.